Hi, this is Somasuri Kinbam from NIT Manipur. Today I will be talking about the effect of size polydispersity on static properties of ionic liquids, a molecular dynamics study. Ionic liquid is a liquid consisting entirely or almost entirely of ions. The credit for discovering ionic liquid is given to this guy, Paul Walden, for his discovery of ethyl ammonium nitrate, which is liquid at room temperature. Unlike our well-known table salt, which is also made up of only ions, it is solid at room temperature, while ionic liquid is aluminum nitrate, and this BMNTF2 is liquid at room temperature. Some well-known characteristics of ionic liquids are low volatility, low vapor pressure, large electrochemical window, high thermal stability, to mention a few. It is sometimes called the designer solvent for its ability to give unique properties by combining different ion pairs. By polydispersed system, we understand it to be a system having variation in size of particles, and if there is no variation in and all the particles are the same, then we call that to be monodispersed. Our polydispersity index is defined as standard deviation over mean times 100 in percent. But why are we considering a liquid to have polydispersity in size? This can arise due to mixing large number of ionic liquids. Mixers also offer the opportunity to fine-tune properties of the system. So, we ask the question, what changes in the properties will occur if the polydispersity index is changed? In order to study this, we perform classical molecular dynamics simulation using the LAMMPS package. We considered 2500 number of particles in which there are equal number of cation and anions. Between each particle, the potential is said to be Lennard-Jones and Coulombic potential combined by giving the expression here in the middle inside the box. The units are set in real units, and the size of the cations are set in 5 angstrom, while the anion size is drawn from a normal distribution with mean 10 angstrom and varying variances giving polydispersity index 0.3% up to 12%. Here in the figure on the left, we see a distribution of anion size for polydispersity index 12. On the right side is simulation snapshot of our system in the solid phase as well as the liquid phase. Results analyzed include tracing of hysteresis loop by plotting enthalpy versus temperature as well as specific heat versus temperature, where enthalpy and specific heat is given by these two formula on the left top. From here, the transition temperatures, namely on cooling as well as on heating, are determined, and the theoretical melting temperature is determined using this formula Tm. These transition temperatures are plotted against polydispersity index as shown in figure A, which is in the middle, and from here we see an increasing polydispersity index, the transition temperature decreases. This may be due to increased separation between ions results in weaker Coulombic interaction. And this hysteresis loop area is determined and is plotted against polydispersity index. From here, figure B, we see that increasing polydispersity index decreases the hysteresis loop area. The spatial ordering is studied by plotting the radial distribution function given in this expression here. From these figures A, B, C, and D, which are the radial distribution function plotted against distance for anion and cation in liquid and solid phase. From here we see that increasing in polydispersity index resulted in shifting of peaks towards the left as we increase the polydispersity index. These results can be used to tune the transition temperature as well as hysteresis behavior, and it may be relevant for designing energy storage material based on phase change materials. Lastly, I acknowledge National Institute of Technology Manipur for the financial assistance. Thank you.